Hello. We present CVRecon, Rethinking 3D Geometric Feature Learning for Neural Reconstruction. Monocular 3D reconstruction is a fundamental task in computer vision with wide-ranging applications. Existing volumetric-based methods suffer from a critical limitation where the image feature is in the 2D while the reconstruction target is in 3D. Due to the lack of depth information, previous works simply duplicate the 2D features along the entire camera array to the 3D space. When 2D image features representing object surfaces are placed in empty or occluded spaces without differentiation, it can complicate feature fusion and geometric reconstruction in later stages, introduce noise and limit the model's ability to predict fine geometries. In this paper, we propose to directly construct a novel ray contextual compensated cost volume (RCCV) as a 3D geometric feature representation, which is an improved multi-view cost volume. The global 3D feature volume can be obtained by tri-linear grid sampling from our RCCVs. Compared to the existing back projection mechanism, our novel 3D geometric feature learning scheme unleashes a greater potential for the downstream prediction models to generate clear fine details. Based on the RCCV, we present an end-to-end 3D neural reconstruction framework named CVRecon. First, the 2D image features are extracted to build standard multi-view cost volumes for each keyframe, which is later enhanced by our ray compensation and contextual in-painting modules. We tri-linear grid sample and fuse the RCCVs as a global feature volume, and the TSDF reconstruction is later inferred with 3D convolutions. To build the standard cost volume, we associate several reference image frames to each keyframe. The reference frame image features are wrapped with different predefined depth hypotheses. The cost volume is composed of the feature matching confidence between wrapped reference frames and the keyframe, encoding the depth probabilistic distribution. The standard cost volume is later enhanced by our ray compensation module. Here we visualize the camera ray distribution in the cost volume. The highest matching confidence position within a camera ray is more likely to be the object's surface. However, these distributions have multiple peaks and the values are not normalized in magnitude. If the local cost value is used for inferring the geometry without the overall distribution as a reference, we observe that the model tends to decode local maxima as the object surfaces and cause the floating artifacts. To solve this problem, we propose to fuse all depth planes to build a camera ray feature, which is duplicated and concatenated into all depth planes of the standard cost volume to form our ray compensated cost volume. With this camera ray compensation, we eliminate these floating artifacts and generate more clear geometries. Our contextual in-painting module is later employed to improve the robustness of the ray compensated cost volume. As shown in this figure, we observe the cost volume fails to encode any useful information in the non-overlapping regions and is excessively noisy in areas with low contrasting textures. We propose to additionally fuse the 2D CNN features into the ray compensated cost volume to form our RCCV with improved robustness. To summarize, our contributions are as follows. Firstly, we identify fundamental limitations of the existing feature learning scheme in the neural reconstruction field and accordingly propose to leverage the multi-view cost volume as a direct 3D geometric feature representation. Secondly, we observe the widely used standard cost volume lacks the distribution reference information along the camera array and propose the ray compensation mechanism to solve this problem. Thirdly, to improve the robustness of the cost volume in the non-overlapping and low texture areas, we propose a novel contextual in-painting module. Lastly, our extensive experiments show the effectiveness of our proposed RCCV and its agnostic nature with downstream fusion and prediction models. We quantitatively evaluate our method on the ScanNet dataset following the widely used 3D mesh evaluation metrics from Atlas and Transformer Fusion. We outperform all of the existing methods by a large margin. Moreover, we would like to point out that the default 5 cm threshold for the F1 score is too large to adequately capture fine geometry details. Smaller thresholds like 2 cm demonstrate much higher improvements. On the 2D depth metrics, we outperform all other volumetric methods by a large margin, and even all the depth-based methods on the absolute difference metric. We further apply it to the Atlas framework to verify the generalization ability of our ICCV and its agnostic nature to the downstream modules. Next, we show qualitative comparisons. We first compare with the state-of-the-art volumetric method Vortex. Note that the only difference is we use our ICCV as the 3D feature source, which leads to significantly clear geometry details. We also compare our method with the state-of-the-art depth-based method CVRecon. The lack of translation parallax in narrow spaces like the upper sample and the faraway texture-less walls in the lower sample will lead to severe inconsistency and degrade the performance of the depth-based methods. In contrast, our holistic prediction generates a clear and coherent reconstruction. We hope this paper provides valuable insights into the development of effective 3D geometric feature learning schemes. Thanks for watching.